Uh, Amit, you're speaking on mute. You need to unmute yourself.
Sorry. Good evening, everyone. Welcome to another session of the network seminar series hosted by the Center for Network Intelligence at the ECE and RBCCPS ISC. So today's talk by Koyel Mukherjee, she will be speaking on towards optimizing storage cost on the cloud. Koyel Mukherjee is a senior research scientist in Adobe Research, Bangalore. Her current research interests are in the areas of efficient generative AI through algorithmic and learning-based approaches. Earlier, she has studied several cost optimization problems in enterprises systems, such as storage cost in cloud and data redundancy in data lakes. She regularly publishes in top CS conferences such as ICDE, SIG MOD, and ICM. Prior to Adobe, she has been a part of Xerox Research as well as IBM Research, Bangalore. Before we move on to the talk, we would like to request everyone to subscribe to our Google group for the information on future talk. You can also visit our website for the more detail from the chat box. Please do check. Finally, we request the online audience to keep your microphone silent for the duration of the talk. And for the questions, you can unmute yourselves and ask directly or post in the chat box so that we can rely on them. Over to you, ma'am.
Thank you. Thanks for inviting me for this seminar series. Let me share my slides. My slides are visible?
Yes, it is visible.
Okay, yeah. So as was mentioned in the intro, my current research interests are in efficiently optimizing the use of generative AI. But this talk is about slightly older work that we did at Adobe Research, where we were working towards optimizing storage costs on the cloud. So this was presented as a research paper in last year's ICDE. So this was joint work with my colleagues, Ronak and Shiv from Adobe Research, and with a bunch of very bright interns that we worked together with, Karanpreet, Khushi, Harsh, and Kavya, and also my ex-colleague Ayush, who since then went on to do his PhD after his stint in Adobe Research. So yeah, spiraling cloud costs are no surprise, right? Data costs are rising for all enterprises humongously all across the world. This is huge amount of data that is being generated daily. This is leading to very high storage costs from this costs on the cloud because most enterprises would be either availing the services of cloud storage providers and or providing on-premise itself is also very costly. So storage costs for data are increasing worldwide for all enterprises. And along with it, the compute costs are also insanely high, and as are the data processing costs. So in fact, if you can see this infographic on the right, IDC had predicted the trend of data rise is exponential as far back as 2018, and the data was projected to reach zettabytes by 2025. Then there would be several, there were like several surveys which have shown that optimizing the spend on clouds is among the top initiatives for several organizations, top organizations in the world. So why is this such a problem? So one of the key non-trivialities is this multi-tiered cloud storage that is provided by most cloud storage providers. So you can see this from this table, which we took directly from Azure's data lake website, that the storage costs vary exponentially from the premium to the archive layers. Like premium, it is like $0.15 per GB, but archive, it's like 0.00099. On the other hand, the read costs vary again exponentially, but in the opposite direction. They increase exponentially in the other way. Moreover, the latencies are also widely varying across these different tiers. So which tier do you use? And most organizations, to play safe, they tend to use, or they end up using this hot or premium tiers, because that way, while you're paying a huge premium on the storage cost, at least you are assured of very low latency. And the read costs are also not high. And since you don't really know which data is going to be read how much, they just play it safe and go for hot or premium tiers and ensure that at least they get the very good performance so that the customers are not affected. But then there's this other non-triviality that the data access patterns vary widely across different data sets, different customer orgs in any enterprise. For example, these are some stats that we mined from our own data lake. So you might be aware, Adobe has this Adobe Experience platform. They provide data management services to various top customers. So we analyzed the data access patterns through some proxy of data accesses that we could lay our hands to. And this is the pattern that emerged. So we can see that most data sets are rarely accessed. I mean, only about 6.5% of the data sets account for 82% of all the accesses. And around 83% of the data sets from the same customer have zero accesses over a certain period that we examined. Moreover, if you look at the chart on the right, this shows the access frequency and how it varies as the age of the file increases. So we see that after about 3 to 4 months of age, that particular file in a particular data set is hardly accessed. So, I mean, just to give some context, so you can think of it as this iceberg kind of data arrangement structure, where a data set consists of these partitions, or which correspond to the batches in which the data were ingested. And in each partitions, there are several files which have been ingested in these batches. So we can see that one data set can consist of huge number of files, and these files can have varying ages. And all of these files from all of these data sets are currently stored in hot or premium layers. So many of these data sets themselves are never accessed at all, but they are just lying there and we are paying a huge storage premium. And then there are many of these data sets where many files are hardly accessed at all because they have aged. And yet we are all storing them in the hot or premium tiers and paying a huge premium for them. Then there would be other non-trivial patterns that one can mine by looking across the different data sets, the different customers, the different services. For example, in some cases, the read accesses would be decreasing over time. In some cases, the read accesses would be relatively constant over time for certain data sets and certain services. In some cases, they would be varying periodically. So it's a non-trivial problem that we want to address. Now, why multi-tiering becomes so difficult? So many cloud providers sometimes provide certain rule-based lifecycle management. In other words, after say X days, 30 days of inactivity, you just push the data to a cooler tier. But such rules easily fail in enterprises because of certain seasonality and periodicity in access patterns, such as year-on-year analysis. Say there is some revenue analysis that needs to be performed by marketers at the end of the month. And maybe they do it at the 31st day of every month. And they pull up all the files. So if this rule is in place, you would push all of the files to the cool tier after 30 days, and then immediately push them back again to the hot tier on the 31st day, and incur a huge charge of moving this data across tiers. And it will ultimately end up being expensive to the customer and will incur latency possibly. There can be other intuitive rules as well. What if we cache the most recently accessed data in the hot tiers? Again, these fails. Suppose caching is indicative enough that, okay, this data will be accessed. The data which was touched in the last 30 days will be accessed in the next 30 days again. However, even that knowledge is not enough to determine what should be the right tier of the data. Because even if you know for sure that this data set is going to be accessed 5 times in the next 30 days, it is not clear that the hot tier is the best place for it. That actually depends on a non-trivial optimization problem, because the exact cost will depend on the size of the data, how much data is being read, in what frequency it is being read, and so on. So only considering the access related information is, or number of accesses that we can expect, or any accesses, if at all we are expecting to this data set in the next 30 days, that is generally not enough to decide that the data should be stored in hot tier or not. So the optimal storage tier, as I was just saying, it depends on this sort of non-trivial trade-off between storage costs, access cost, the type of access, the amount of data that is being read in each access, the frequency with which this access is happening, the actual cloud tier cost for storage, the cost for the tier change, and what are our SLAs with the clients. That is also very important. For example, if you know that certain data is good enough to be in the cool tier with certain access patterns, we might still need to keep it in the hot tier because of our SLA with the client. Now, what is SLA? It is the service level agreement that we would have with the client, which might be that we need single digit millisecond latency. Now, that is only guaranteed, say, by the premium layer. So whenever, however little that client would be accessing the data, we would need to pay that premium based on our SLA and would need to store that data in the hot tier. So SLAs with the clients, along with all of these factors, need to be all accounted for when we decide on the optimal storage tier for a particular data. Now, data partitioning and compression. So can we look into a more effective partitioning of the data and compressing the data in some way to reduce our storage costs? So data sets are often large. Like in our enterprise, for example, we often come across data sets of the order of terabytes. But whenever a data set is accessed, it is not that the entire data set is being read. It is not that all of the files in the data set are being read. Certain parts of the data or certain files generally end up being more important or more heavily accessed than the others. This can be either temporal information, like it is the most recent files, or it can be some file containing very important information for making certain calculations of, say, revenue or something. Yeah, so I'm not an expert on that, what files are generally important for marketers and analysts, but it is often clear that not entire data set is being read every time a customer is reading a data set. Think of it, right? If you're issuing some sort of an SQL query, you generally read certain columns, and filter it by certain conditions, only reading a portion of the data. And only certain portions of the data are generally more important. So people have started, by the time we did this work, workload-aware data partitioning schemes were already being explored, but most of them had the issue of scalability. They were not scaling well as the size of the data set was increasing or as the query workloads were becoming richer, and they were not dynamically adaptive in nature. But it is very important to have a dynamically adaptive data partitioning scheme because the workload itself can be dynamic. The trend of the workload, the type of the workload, or the distribution itself might change over a period of time. Now let's consider data compression. Now compressing the data might very well reduce its size and reduce your storage cost, but it will potentially add the overhead of decompression. And that can increase the latency to access the data as well as the compute cost that you might incur. Now, there were certain efforts which were enabling efficient queries or analytics directly on the compressed data, but these are more efficient and popular for read-only datasets, which is not the case for most enterprises. The datasets are often evolving, so we cannot have schemes which are only suitable for read-only datasets. So this brings us to the problem and its motivation. So the motivations were cloud storage, cost, and performance considerations in our Adobe Experience Platform Data Lake. which was caused by huge volumes of customer data sets generated by time series events or event logs. And this data resides in the cloud, different cloud providers we use. In this work, we focused on Azure. We get a breakup of costs from the cloud service provider at the end of a billing period, say a month. And this cost is billed or incurred for storage over a period of time and per every access. So considering all of this information, we wanted to optimize the total costs at the end of a billing period, say K months, so that our cost to the organization reduces through three different strategies: optimal multi-tiering, data compression, and data partitioning. So towards that, we broke down our problem into these following sub-problems. The first one we called opt-assign. Here,
So one clarity, this data partitioning is required because even if you don't access the full data, certain files inside the data, you have to pay the full cost for that data, right?
yeah, so what happens is data partitioning, if you do not do any sort of a workload-aware data partitioning, for the entire data set, you will be taking a decision, right? Say storing it in the hot tier or the cool tier. Now,
Right.
suppose a small fraction of that data set is being accessed very frequently. Now, to you, if you look at the macro data set level information, to you, it would seem that that data set is being accessed very frequently. Hence, your logic should be to keep it in the hot tier or premium tier. But there is a large part of that data set that is not being accessed frequently, and yet you are paying the premium for storing it in the hot tier because you have not done a workload-aware data partitioning. Yeah. So that was our motivation. Yeah, I'm not saying that this is what is done currently in Adobe or in any of the enterprises, but at least this is definitely a gap that can be explored by enterprises, and at least the research showed that there is significant gain to be achieved.
Yeah, thanks.
Yeah. So yeah, opt-assign, the first sub-problem. So here you are given a prediction for the volume of accesses for a data set for a projected period. You can consider it that the data partitioning by data set, I mean at this stage, that we are considering data partitions. So for each data partition, you already have some prediction of their accesses for a projected period. Given that information, what is the optimal, in expectation, assignment of tier and compression scheme per data set or partition of data set while maintaining the latency and capacity requirements? The second problem is compredict, which looks into the data compression. So the first problem is already doing the assignment of tier and compression scheme, right? But for doing that, first we need to know how a particular compression scheme is going to fare on a particular piece of data. So compredict tries to accurately estimate the compression ratio and decompression time that would be incurred for different compression schemes on various data sets or data partitions. Then we come to the data partitioning, where data part tries to do an access pattern aware, optimal and efficient partitioning of the data. And finally, scope is what we call this unified pipeline for storage cost optimization with performance guarantee. Now I'll go through each of these subproblems one by one. But before that, these were the data sets and workloads that we worked with. So the first one was enterprise data. Here we had access to two sets of enterprise data. The first one was coming from this data lake, ADLS Gen 2, where we had hundreds of data sets ranging from terabytes to petabytes for several customers. In this case, we have only access to the metadata and the historical access logs at dataset level. We do not have file level accesses. We do not have any access to the contents of the file. In the enterprise data 2, this was a much smaller data that we were able to extract with full information. Here we have full access to the data, but here we do not have the access logs. Hence, we generated queries for this based on a skewed Parlaw Zipfian distribution. We also use TPCH data 4 variants There were like 8 different tables with 22 different complex queries. And for each template, we generated 20 queries. And we considered different variants of this. One was with uniformly generated data. One was with Zipf skew with a high skew factor. One was a much larger scale data at 100 GB, and another one was a terabyte scale data. So now coming to the problem opt-assign, where we are trying to optimize the overall costs. So this determines the optimal assignment of the tier and compression schemes given data partitions with predicted number of accesses for a projected period. So we formulated it as this integer linear program, and I will not go into the details. I mean, please feel free to look up our paper to get the details, but I'll just try to explain it at a high level. So what this is doing, the first let's look at the objective. So it is trying to minimize the overall costs. So what do we mean by overall costs? First is the storage cost that you will be incurring for a particular data set at a particular tier. Then the second would be the read costs. Then they would be the write costs for the data. And if you are compressing the data, then you also have to account for the compute for the decompression for the data. And we also want to look into the compress sizes on applying the compress cost. So this like SPPN would be the span or the size of the nth partition. RKN would be the compression, the kth compression algorithms, compression ratio as predicted on the nth partition, and so on. Then rho PN is the predicted number of accesses. CC is the compute cost. DKN is the decompression predicted for the kth compression scheme. CLR, this is the read cost, and then there is this first storage tier cost, CSL, and we also have the tier change cost or write cost captured by delta L. So please refer to the paper for the details, but this objective term is trying to capture all of the different costs that are coming, the storage cost, the access costs by read accesses, the write accesses, accounting for both the size of the data partitions as well as the compression ratios as predicted by the different compression algorithms, as well as the decompression times and the associated compute costs by different compression algorithms. Now, what are the constraints? We want every data partition to go to one tier and have one compression scheme assigned to it. Now, note that one compression scheme can also refer to no compression. That can also be one of the compression options. Then we have this capacity constraint. So suppose we have a capacity constraint per layer. If there is some sort of an agreement of the enterprise with the cloud service provider that for the Lth tier, SL is the total amount of capacity or storage capacity that can be used, then this is the constraint that is capturing that. Note that in many cases, this is actually infinity. We do not have a per tier storage capacity agreement. Also, we could modify this to have an overall capacity limit across all the tiers. This constraint can also be modified to account for that. And then the last inequality is to account for the latency that we can tolerate for that particular data partition. So how do we get that threshold? So that will come from this SLA or the service level agreement that we would have from that particular customer and the particular service which is accessing that data set. And the type of the service means the type of actions, the particular software that is accessing the data set, and which customer is it originating from, what agreements do we have there. And this latency should take into account both the tier latency, which is BL, as well as the decompression latency if we are using the kth scheme. So this is a complicated linear program, and we show that this is strongly NP-hard by a reduction from 3 partition. However, you can also appreciate that this is a pretty generic framework and can easily be modified to handle these multiple scenarios, as in different latency constraints or no latency constraint, either no storage capacity constraint or a storage capacity constraint and so on, no compression scheme or any particular compression scheme and so on. So now, since it is NP hard in the most general case, we try to consider certain special cases for which we can come up with polynomial optimal algorithms. So the first special case, which is actually an important case for enterprises, is when the data partitions are equal in size and there is no compression scheme. So in this case, we show that we can model it as a bipartite matching problem and solve it using a minimum weighted bipartite matching algorithm, the Hungarian algorithm, and polynomial time to get the optimal solution. So to understand it is because all the data partitions are equal in size and there is no compression, we can actually consider them to be unit size and accordingly, sort of scale the tier sizes that we are using. And now for, we can sort of create copies of the tiers. Actually, maybe I will, the details of this will again take a lot of time, so I'll refer you to the paper. But what I mean is because these are equal size data partitions without compression, we can consider them to be unit size, and therefore the problem becomes polynomial in size with which can be solved in polynomial time using matching. And finally, we consider another simplification where everything is same as the generic problem, but there are no capacity constraints. Just going back to the previous slide. So everything is same here as here, but this capacity constraint becomes infinity. So here we actually show that a greedy algorithm can be shown to give the optimal solution for all cases. So this is very practical because greedy algorithm can be applied in linear time. It's a highly scalable solution. And it is actually relevant to most practical scenarios where we do not have any storage reservations per tier or any storage reservations overall. And this was the particular case that we faced in our enterprise setting as well. So finally, we ran our experiments with this greedy algorithm. But for doing this, we first need the access patterns. So how do we do that? We first predict the optimal. So predicting the actual access patterns becomes non-trivial because they can highly vary. These are doing this as a, there's a question.
Sorry, ma'am. Can you please go back to the previous slide? Yeah. So in this bipartite graph, can you please help me pass what are these nodes U and V?
Yeah. So you can think of these as the data partitions. These are all unit size. And the V's you can think of as the nodes corresponding to the tiers. So now, at most from each tier, for each tier, you can have all n partitions going to it, right? So you will have at most n nodes corresponding to a tier. And these edges, Wij's, what they are trying to capture is the cost as captured by this linear program for storing the ith data partition in the jth tier. So, for example, if you have 2 tiers, then you will create for each of these tiers, say n copies. Now, the same data partition UI for going to tier 1 would incur a certain cost based on how frequently it is being accessed and so on. And if there is some cost associated with the latency and something. And similarly for tier 2, it will incur another different cost. And in some cases, some of these edges will not even exist. It will not even be feasible. For example, if UI is from a highly premium customer and tier 2 causes a latency which is not acceptable for that premier customer, then that edge will not even exist. So some of these edges will exist and some of these edges will not exist, and the weights will vary based on their access patterns and the particular tiers cost structure. So you ultimately get this weighted bipartite graph where you can solve minimum weighted bipartite matching using Hungarian algorithm.
Thank you.
One minor question. What is the insight or the reason behind equal size partition for enterprise customers?
So you can set certain parameters which will say for ingesting this data connectors, right? Maybe you can say that each batch will be ingested up to say so many MBs or something, right? I mean, maybe these batches will be ingested in 4 MB or whatever. So you can think of this as equals as partitions. Maybe some batches will not be full 4 MB, but you can consider to pad them and just as an approximation in this case.
Thank you.
So yeah, predicting access patterns. Predicting the exact access patterns turned out to be a non-trivial problem, and we often don't even have that much data for doing that. So what we actually try to do is we try to predict the optimal tier for the data sets directly using the historical access logs and our opt-assign module. And we trained a random forest model on this data, which turned out to be pretty good. We got a pretty high F1. So we use the features as the size of data sets, the month since data set creation, aggregated monthly read and write accesses for last few months to train this random forest model. So again, try to explain this. What we did was we directly tried to predict the tier using whatever, we use as a training, the size, whatever aggregated monthly read and write data sets, and we use in the training data we have for the projected period, we also have the optimal tier as calculated by opt assign, which I was just explaining. So now using that as the label of the data to train this random forest model on the test data also for a later period of time, we were able to achieve a pretty good performance on this RF model. As you can see from here, this confusion matrix shows pretty good results. This was done on about 700 terabytes of data in 760 data sets. And here we compare our results with predicted or known access information with intuitive baselines. So you can see that when we have known access information for a period of 6 months, the amount of benefit we can achieve is about 43.8%, which is a huge cost benefit. So here are some more empirical results that we had. So here we use the data sets themselves as the data partitions, and we projected the access patterns for 6 months using the historical access logs with pretty large data sets, terabytes to petabytes. And we saw that the cost benefits are ranging like pretty high from 49.6 to 83.69. And from these charts, we can see that as the number of read accesses are lower and lower, for those data sets, the cost benefit really jumps up high. Also, the data sets from the chart on the right, you can see the data sets need to be of a minimum certain size for you to start seeing the benefits. If they're very small, the cost benefit is low. But as the data sets achieve a certain size in GB in range, the cost benefit sort of becomes pretty large. So now coming to the COM-PREDICT problem, which is the compression predictor. So here we estimated the compression ratios and the decompression times for data partitions on the fly. We considered several popular compression schemes such as gzip, snappy, LZ4, quick LZ, and so on. And we also considered different data storage layouts, which often can have a big impact on your compression performance, both row store and column store. We propose this weighted entropy feature for each partition P, corresponding to each data type in P. And we were again able to achieve a pretty good performance with XGBoost and random forest as of the observed on the TPCH-Q data on different layouts, both gzip and Parquet plus gzip and so on. So now coming to the data partitioning part. So this is the access-aware data partitioning that I mentioned initially. So what this solution to this part does is it generates the initial data partitions in an access-aware manner and then merges overlapping partitions optimally. The goal is that the total scan or the read cost incurred by queries is within a certain limit, while the overall space is minimized. So what do I mean by this? So if you look at to this figure, data set 1 and data set 2. So this maybe F1, F2, F3 was one partition generated in access aware manner. Then F3, F4, F5, F6 was another one. F6, F7 was another one. Note that there is some overlap between these. So we can, in principle, merge some of these partitions so as to decrease the number of scans or the read cost incurred by queries, while the overall space is minimized. So, I mean, obviously, merging will not decrease your number of reads, but the overall space can be minimized, right? Because, for example, if F1, F2, F3, F4, F5, F6 is now considered as a single partition, then F3 and F6 will not, I mean, if this entire thing was, for example, F1, F2, F3, F4, F5, and F6 was a single partition, then F3 will not be replicated. So you are saving some on the storage cost. So you have to see how much this savings of the storage cost by merging partitions, what is the trade-off with the total scanning cost or the read cost that is increasing because of this. So again, we formulate this as an integer linear program. So MK is what we want to determine as our optimal set of partitions. And we want to overall minimize the space taken by these partitions. But we have the constraint as given the access frequencies for these partitions MK, the overall read cost should be under a certain threshold. And every file should be part, or every small partition should be at least part of a bigger partition. You should not leave out any partition. Yeah. So, yeah. So this problem is strongly NP hard again by reduction from another problem which was studied by Huang et al. From VLDB 2017. So we tried to come up with a heuristic to solve this problem. So we formulate this problem as a graph problem where these nodes are the initial partitions. So you might actually ask, like, how do you come up with the initial partitions? So the initial partitions, actually, you can come up by doing an analysis of the query logs. So from the query logs, we can see that there will be certain query families which are accessing the same set of rows, maybe different columns, but same set of rows again and again. So those queries families are constituting our initial partitions. But as expected, there can be a lot of overlap between them. So this U1, U2, U3, U4, these are these initial partitions. And now these edges between them sort of capture the benefit of merging, or the cost and benefit of merging these two nodes. So there will be a certain cost of merging them and a certain benefit. So this ratio of the benefit to cost is being captured by this edge weights. And now we try to do a greedy sort of graph merging or partitioning by this algorithm G part, where it is first trying to figure out, it is storing these edges as a max heap. And first, it will pick the pair of nodes which are most beneficial to merge. It will merge them, and it will remove that edge from the heap. if that size of the merged node is still under a threshold, then it will sort of go back. It will create the edges from this node to all the other nodes as well, and those edges sort of go back to the heap. You heapify again, and you then select the next most beneficial pair of nodes to merge. So you sort of continue this way till you are left with certain singletons, which you sort of merge together, or your heap is empty. So while we don't have any theoretical results on this, empirically, we were able to show that this is able to achieve a very good trade-off between the cost of merging and the fraction of duplication, which is sort of, in a way, the proxy for the benefit for merging those two nodes, as shown by these graphs here. So for the special case where the partitions are actually ordered, as in there is a sort of contiguity in these partitions, even if there is overlapping in between them, for that special case, we are able to present a dynamic program which will solve this optimally with certain guarantees. So consider that an optimal solution for n partitions with a cost threshold of C opt would require a space S opt. Then we give this dynamic program, which will find a solution which will take a space less than equal to S opt, but with a cost at most 1 plus n times epsilon C opt in order n square n plus 1 over epsilon time for any fixed epsilon greater than 0. And for epsilon 1 over n, this is actually giving us a 1-2 by criteria approximation of S opt and C opt in order n cube time. So this actually proceeds by this bucketing in terms of epsilon buckets and solving it as a dynamic program. I'll omit the details for in order to respect time. So actually, this brings me to pretty much the last slide I have here, which is the unified pipeline. So far, we talked about these various things. We first talked about opt assign. So which is, if you're given that each data partition is going to be accessed so many times in the next few months, and this is how all the compression algorithms, you already know that, will behave on all of your data partitioning algorithms. These are all the parameters of cost. Then opt assign will solve you optimally how to store the data partitions and with what compression schemes. But for doing that, we need to estimate. First of all, that becomes an NP-hard program. So with certain relaxation, which is the relaxation that there is no per tier capacity requirement, which is the case in enterprise setting, we were able to solve it with a greedy algorithm. But there are two things. One is, how do we get the compression performance there? So for that, we had to train this random forest model, which helped us estimate accurately the compression performances of these various algorithms and the decompression times that they would take on these various data partitions. We also had to estimate what are this number of accesses. Now, actually, that becomes a very difficult problem. And the final problem we ended up solving for that was we actually created a label data set where for the training data set, given the access, known accesses, size of the data set, all the cloud parameters and everything, we were able to label it optimally. What should be the optimal tier? And then using this labeled data along with the features such as data set sizes, aggregated accesses, reads and writes, and so on, we were able to train this random forest to give us pretty accurately what would be the predicted tier of these data sets for the projected period. And then we came to this slightly orthogonal problem of data partitioning, which is the first set of problems sort of assumes that data partitioning has already been done for it. But what if the data partitioning itself is not optimal? So there we brought in this workload-aware ideas, where we are sort of coming up with this initial partitioning of the data set based on analysis of query families, And then we are merging overlapping partitions so as to reduce duplication in the system while keeping the total access costs, the read costs under a certain limit. So finally, putting all of these together, like first doing the data partitioning and then solving this OptiSign along with ComPredict. This is what we call a scope, storage cost optimization with performance guarantee. So we compared it with certain baselines in the literature. Now, we did not find a direct baseline in the literature for this exact problem. So we adapted certain closely related methods for this. So you can find the references in the paper for each of these algorithms. So you can see that for multi-tiering, we have written Hermes here. So that is an algorithm which only tries to optimize the tier while it does not consider the compression and latency. Whereas H-compress will only try to optimize the latency and not consider the other factors and so on. Sorry. So we can see that scope in general performs much better than any of these baselines, which are these values and these are scope values. But interestingly, if we apply our data partitioning scheme GPart on top of these baselines, their performance also improves. So this shows that the data partitioning by itself is a useful thing to do to reduce the overall storage costs. So yeah, that is all. So that brings me to the end of my presentation, and I'm open to further questions.
Hello.
Yeah.
So this decompression we're talking about. So this decompression will happen on the server side only, not on the local computer where the file has been accessed.
Yeah, I mean, depends on the particular storage providers and your implementation, right? So yeah, if it happens on the server side, then you have to account for the compute cost for that also. And also the latency, yeah, we were not able to benchmark that, but yeah, I'm not sure. There might or might not be a latency implication.
So the compute cost which or the latency which you are calculating is it like from server to the local time, or it's like what how much time does it take to just open it up? Like
Yeah, that. And also the latency, if you remember, the latency considers both factors. One is this time to open it up, of course, and BL factor is the cloud provider's latency as given. We just take that for a tier L. So for certain tier, what is the promised latency to the first byte? So that is what we consider here as BL.
another question is like you talked about the workload aware partitioning.
Yeah.
So like what are like different files kind of partitions, like suppose Excel or PowerPoint or image or just only text like Word. So is there any partitioning happening according to different types of files, different file formats basically?
No, we didn't have this PowerPoint or images or so we mostly considered this time series or event logs in which data is stored from our customers. And these you can think of it as CSV.
Okay, CSV files. Okay.
Yeah. Or Parquet storage. Yeah. So.
Thank you.
So, have you considered hybrid cloud or even multi-cloud in this, or is there any study which is like, for example, you could keep hot data on near storage and cold data on cloud storage, which is cheaper?
Yes, that's a great point. So while we did not consider it in this work, but yeah, I can definitely see, I mean, one can think of extending, for example, this ILP itself, right? To consider one such option, where along with the cloud tiers, I mean, one option can also be the local storage. right, with its associated cost parameters. Associated cost would be, which will be much lower. So yeah, that's a great point. While we haven't considered it in this work, that should be definitely one way to extend this.
So I missed the parameters in this model. So does the model already include transfer costs? Because those are significant, especially when you're talking about multi-cloud.
No, we do not consider any transfer costs between cloud. We do consider the tier change costs, which is in this delta L. So for example, if a certain data was stored in cool and now needs to be moved to hot, there is a certain tier change cost, which is read cost from the cool and the write cost to the hot. So that is what is captured here. So, yeah, but multi-cloud, yeah, probably might require some more modification to that. Yeah, that's a great point, and that is probably a more relevant scenario currently, given that most organizations are moving to a multi-cloud or hybrid cloud scenario.
So one more question on this reducing the or like frequency of access or the
Yeah.
predicting the access patterns. Is there any study on reducing the access just by caching the metadata? So metadata could be just a file characteristics or even slightly more advanced, such as doing a parsing, pre-parsing the data and doing some ETL to cache or store only the like some hotly accessed parts of the data.
Yeah, so I mean, we consider that as one of our baselines here. So here one baseline was hot if the data is accessed in the last 2 months, and hot if data is accessed in the last 1 month. Then also using the optimal tier of the previous month. So, but all of these actually show much lower benefits than the way we try to do it using OptAssign to sort of predict the correct labels for the data, training the model with that. So.
But all accesses are treated equally, right? Like just reading a file metadata as against reading the entire contents of the file or object will be treated equally.
So metadata read, so we did consider the amount of read. I mean, as in the aggregated read. I mean, the total amount of read that has been done from a data set for the last few months. So I don't know if metadata read has a different cost structure than the file content read. I'm not aware of that. I just know the read cost structures as given from this Azure data like ADLS Gen 2. So yeah, so we considered metadata reads the same as file content reads in this case, if there were any metadata reads. Yeah.
And all these files or are they files or objects with some metadata which is stored separately?
These are data sets. I mean, data sets as in you can think of these as iceberg data sets. Yeah.
Equivalent of S3 buckets or something like that?
Data sets would be stored in S3 buckets, right? I mean, if we are talking about AWS. So a data set would consist of several files in our case. Each files would have been, say, ingested in certain ingestion batches as generated by the customers. So you can think of these as event logs, for example, or clickstream events. So CSV files, which have all been, say, ingested periodically. And they are, say, all part of one data set from one customer. That is what is a data set here.
Okay. Thank you.
Other questions?
If no other questions, so we'll conclude this session. So thank you, Koyel, for such an informative talk.
Thank you.
Thank you everyone for joining this talk and have a great evening. Thank you.